So we are going to talk about trig functions and how they relate to all those angles and angles of rotations that we talked about yesterday. So these are our classic definitions of our trig functions based off of our right triangle. So we remember that sine of an angle, now we talk about an angle here, theta, it's one of the angles inside our triangle is what we're relating all these trig functions to. And it's the division of these two different lengths of the triangle. So like sine is the opposite over the hypotenuse. Opposite is across from the angle, not touching it. Hypotenuse is the longest side across from the 90. Cosine was adjacent of our hypotenuse. Tangent, opposite over adjacent. These are things we covered back in Math 2. Now what happens is, we talk about this angles of rotation inside of a unit circle. If we look at this picture here with this unit circle, and we call this our angle of rotation now, we're just say that's our theta. That's like this thing down in here. And we trap this inside a circle that is 1 unit with radius. What happens is we can see this in here, this picture, we get a right triangle if we trace out the x and the y distances to get to that point. And inside this right triangle means that we also have, since this is the angle we're taking relationship to, the y over here would be across from this. This would be our opposite side. This x, because it's next to that angle, would be our adjacent. And then this 1, and we know it's 1 because that's why we're inside the unit circle. It has a radius of 1. And no matter where I actually rotate that thing, that radius is going to stay the same, so the hypotenuse here is always going to be 1. So what happens is we can take this information with these new angle rotations inside and this pinning this thing into a circle. We actually get new definitions. They're actually the same definitions, but they look a little different for our sine function, meaning inside a unit circle, sine actually has the value of y divided by 1. Or just the y value. Cosine is the x divided by 1, or just the x value. And then tangent was the opposite divided by the adjacent. That's the y divided by the x. And one interesting fact about that, let me make that a little bit clearer in my writing, is y divided by x is actually a definition of slope. This is actually the slope of that line of the hypotenuse as we look at it, okay? And what we can do with this, though, is we can take these things and we can extend this to, this is the exact same stuff that we had on the other side, to our reciprocal trig values. So we figured out over here that sine of this was y, cosine was y over 1, this was x over 1, tangent was y over x. We also had our reciprocal trig values. Reciprocal trig values, cosecant, secant, tangent, they were these things flipped over, meaning cosecant is the reciprocal of our division for sine, which means that our hypotenuse goes on the top, our opposite goes on the bottom. Those also transfer over into our unit circle. So this would be 1 over y, this would be 1 over x, and this would be x over y. We won't do a ton with the reciprocal trig values. We're mainly going to focus on our primary sine, cosine, tangent stuff. Excuse me. But just so we know, you can do that with all of them. Because what we're going to explore here is we're going to take this idea of this unit circle, and we're actually going to find out that when we look at our picture with our unit circle here, all the trig values, all the answers for anything we plug in for sine, cosine, or tangent, all of those answers actually exist on this edge of the unit circle out here, even though that's only from angles of rotation from 0 to 90 degrees. Still have angles that are bigger than 90 degrees. So, we stop over here, even though all the actual numbers we get out of plugging in for sine, cosine, and tangent, we'd see them all on this edge between these x's and the y's. We can't have angles that we plug in bigger than 90 degrees, because we've done this before. You can plug in sine of 120 degrees and you're going to get an answer on your calculator, which means there's got to be a way to find this thing. But what happens, and let's actually look at one of these and we'll see what's going on here. So if we take a look at this, we figured out that sine, cosine, and tangent based on this triangle are related to this point. So we still get a point X and we still get a point Y over here. But what happens is when we go to make the right triangle, the similar shape that we have over here, we drop this side down here, our right triangle's over here now. And the angle that we did, the actual angle of rotation, is right here. But that's not the angle inside the triangle anymore. The angle inside the triangle is right here. And what we see is this triangle actually starts repeating itself. Once we get to the first quadrant, we get the same triangles that we had over here in the first quadrant again in the second. Same thing's going to happen in the third and the fourth. And there are actually ways that we can figure out how to refer them back to what triangle we had in the first quadrant and see that those answers repeat. It also helps us understand when we see that these answers repeat because these triangles repeat, it's why the shape of the graph is the way that it is. We remember sine makes these wavy curves that continue on forever. It's because the values come from these lengths of the sides of the triangles that we're dividing. And because when we start rotating, get bigger and bigger angles, because angles are what get plugged into sine and cosine and tangent, we start getting more and bigger angles in here. Well, we're getting the same triangle over and over, so we're getting the same answers. Sometimes they can be negative, sometimes they can be positive. We'd see that because over here in the second quadrant, well, this x is negative over here. And since x defines cosine, it means cosine will be negative over here. So let's kind of continue on with this. Let's look and see what happens with these ideas of these reference angles, okay? So we get this idea. So if we have this same angle, this angle theta, we reflect it over here into the second quadrant, we could easily find this point. This point's going to be xy, but just like we just talked about, this one's going to be negative. And that angle that we're trying to find is going to be in here. Now what we have to do is we kind of got to put blinders onto where we started. We took this angle theta, say it's 35 degrees, if we knew it was 35. We reflect it over here. We want this 35-degree angle triangle to be over here in the second quadrant. What I want to know is, how is that related to its actual angle of rotation this way? So kind of forget about this one for a second. How are these two angles, this theta and this theta prime, equal? Well, what we see here is, well, those two, if we add them together, are going to give us 180 degrees. Meaning that if I want to figure out with my angle of rotation how to find out its reference angle, what triangle in the first quadrant it should relate to, well, theta prime is 180 degrees minus the actual angle of rotation. Meaning that if we did this, I'll draw one out so you can see this. Say we were right here, and we had this angle that was 120 degrees. And we wanted to figure out the point out here on the end, on the unit circle, so we could figure out the x and the y, so we could find sine and cosine. Well, that triangle is actually drawn right here. Now, this is the angle that I need to find. The 120 is on the outside edge of it. I need to figure out what's inside right here, because that's the triangle that I could find the values for over here in the first quadrant. Well, this, based on this formula, that's our theta prime, where I put that question mark. That is 180 minus 120, which tells me that angle in there is 60 degrees. What that's telling me is that the value for x and y up here, I'm going to have the same numbers as the 60-degree triangle in the first quadrant. Only thing I'll have to adjust is that in the second quadrant, that x becomes negative and the y becomes positive instead of both of them being positive. So therefore, when we get into the second quadrant, the only thing that stays positive is the sine value. So that means negatives would be cosine and tangent if I looked at my negative. None of them were negative. And this has to do with the point. The point was both positive, so when we make all our fractions, you're going to get x over y, and then you're going to put ones on the bottom of those things. But here we had a negative x and a positive y. Here we ended up with tangent being the only thing positive, because in the third quadrant, we're down here, this thing's going to be negative x, negative y. Both the x and the y are going to be negative. So when we divide them by 1, we get negative answers for sine and cosine. But when we go ahead and do tangent, we get negative over negative, which gives us a positive. And what we're supposed to see here, just like the first one, we're going to forget about where we started, and this is our theta angle rotation. And here we're looking at what happens if we take theta and we subtract that theta prime. Well, theta minus theta prime, think negative angles, we're going to go back up, takes us back to the 180 mark, meaning that this is 180, and to find that theta prime angle in there, we're actually going to have to take theta and subtract 180 from it. And so the things that are negative here, we ended up with sine and cosine. All right, so the point, if we reflect down into the fourth quadrant here, well, the x is going to stay positive, but now we're down in the fourth quadrant. Our y's become negative. We're still going to get the same numbers. They're just going to have some different signs between the x and the y. So with a positive x and a negative y, we end up with cosine being positive because that's the x. Cosine is related to that x value, but the y makes sine positive, sorry, sine negative. And that means it's also going to make tangent negative because we're going to get a negative over the positive when we do our division. Now here, again, forget about the red dotted line. We're looking, this is our actual angle of rotation, theta. Theta plus theta prime, we see, well, that's going to take us positive angle this way. That's going to take us all the way around to 360 degrees. So if we want to figure out the angle inside our triangle here that relates us back to a first quadrant triangle so we can find the values, well, that theta prime is going to be 360 degrees minus theta. We get these ideas right here. These things are called reference angle formulas. And I've got them nice and pretty on the next slide for us to keep track of. But what we're trying to state here is that all these values for sine, cosine, and tangent that we were talking about here, this x, y, so on and so forth, everything we find on in the first quadrant on this edge, all these x and y values that we used to find these values of sine, cosine, and tangent, all those numbers repeat themselves. The signs just change, which is why we get the oscillating curve look of the sine and the cosine graph. Okay, so and we're gonna find some exact values in here because there's some that are academically important that we want to keep track of, kind of prove our knowledge on this as we work through. So everything kind of in all one big spot because I know that's a lot of stuff going on here. So if theta is our angle of rotation, theta prime is our reference angle, the one that we want to find in our triangle. If we're in the first quadrant, we don't need to do anything because what we're trying to do is we're trying to take these angles that are bigger than 180. So down in here, these are, I'm sorry, not bigger than 180, but bigger than 90. These are going to be, this theta is going to be bigger than 90 degrees, which means it would be tough to fit the triangle. And we're going to relate these angles back to triangles that were in the first quadrant. So that's why we don't need any reference angles for anything in the first quadrant. I have them written for radians here as well, but I think they're much easier to remember in degrees. If something comes in radians, just divide it away. Or I'm sorry, not divided away, converted away into degrees. It's much easier because our brains are wired to think in degrees after we practice forever. This is a way to help remember what's positive and negative in each quadrant. We say that all students take calculus because all, the letter A tells us in the first quadrant, everything is positive. Students, S tells us sine is positive in the second quadrant. Take, tangent is positive in the third. Calculus, cosine is positive in the fourth. And what we do is we use reference angles to find the values of sine, cosine, and tangent based off what we saw in the first quadrant. And we're going to learn how to do those in just a second. And we can adjust whether they're positive or negative based on which quadrant they fall in. Okay? So we're going to practice some of that right now. So what we're going to work on here is we're going to work on finding some exact values. Now this could get a little bit tricky as well. Okay? So to do this, we got to remember some of our special right triangles that we learned way back in Math 2. And I know it's been a long time, but there were special right triangles that there were relationships with. And if you remember back in Math 2, that's awesome, but I don't expect anybody to, because it's something in Math 2 we covered for just a little bit of time. And it didn't really make a lot of sense because we didn't know what we were going to use them for. This is what we use them for, because it helps us define these units, these values in the unit circle. So there's only a couple special things we need to remember. We got a 30, 60, 90 right triangle, and what we say here is that all these sides, if we know these angles are 30, 60, 90, we know that there's a common factor between all the sides of A, and multiplying some of the sides by specific numbers like the 2 or the root 3, we can find all those lengths, meaning that if I knew, for example, that A was 1 for this, well, that means that this side would be 1 root 3, this side would be just the number 1, and this would be 2 times 1, which would be 2. And I could substitute this different number in for A. I could put 2 in there, I could put 3, I could put the square root of 7, anything. And I'd be able to find all the lengths of the sides if I knew I had a 30, 60, 90 degree right triangle. We could do the same thing for this 45, 45, 90. Has a different set of relationships based on the fact that we know these angles. 7 a number for A. You can find all the lengths of sides. That's what we're going to do here. So the first exact value we're going to look for is we're going to work with this first angle of rotation of 30 degrees. So that means that this is 30. And since we know, right, our x is down here, our y is here, what we want to find, because we want to find the sine, cosine, and tangent at 30, we want to figure out what the value of the points is out here, because we know from what we just saw that the cosine is x and the sine is y, and the tangent is found by dividing the y value and the x value. So we're going to relate these exact values back into this. So let's look at this just as the triangle. So this is 30. I know this is a right angle. So that means this has to be 60. So the way that this works is we're going to use these relationships. Why do I know this is 1? Because I'm in the unit circle. So that guarantees that that radius is always going to be 1. So that means that this number up here has to be 1. Because of this special right triangle that's formed by this angle of rotation of 30, that means that this is 2A up here, and out here on this side across from the 30, this is A, and then this is our A root 3. And what that allows me to do is that's going to allow me to find this A value, because this number out here, this is the Y. This is the x, and once I know that point, I'll be able to find these values of sine, cosine, and tangent. So I can do this because of this one right here. This tells me that 2A is 1, so therefore A is 1/2. So that means that this number right here is 1/2. And then this number over here is 1/2 times root 3, which is root 3 over 2. So that means my x value, my x length down here on the bottom, this is the square root of 3 over 2. My y length over here is 1/2. So this coordinate is the square root of 3 over 2 and 1/2. And since the sine value, this is equal to the y of that coordinate, this is equal to the x, that means the sine of 30 is going to be the square root of 3 over 2. The cosine, I'm sorry, I stated that incorrectly. The sine of 30 is the y value. It's 1/2. The square root of 3 over 2 goes down here. Now the only thing I need to do is I'm going to actually need to divide these two numbers, and I'm going to want to get these things exact because that's one of those things we have to do with this. So this is going to be 1/2 divided by square root of 3 over 2. Now we're going to keep it, change it, flip it. And that 2 goes away. So I end up with 1 over the square root of 3. But I can't leave that square root of 3 in the bottom. So I've got to rationalize it by making a fraction with it. Those multiply together and give me 3. I get square root of 3 on the top. So that is square root of 3 over 3. And these are the exact values of sine, cosine, and tangent of 30. Now what we'll see as we work through this, though, after we find all of these ones in the first quadrant, knowing these exact values in the first quadrant means that I can relate those to all those other reference angles, triangles that have that same 30-degree inside that edge of the triangle, meaning that when I go and I find one in the second quadrant and I find that the triangle that's actually made has a reference angle of 30 degrees, I should get the exact same numbers. I just have to flip the signs. So let's try this with this 45. So same idea. Here's our 90. We want to find this coordinate up here. So we know this side is 45 and the other side's 90. So that's going to leave us 45 here. And same reason up here. 1, we're inside that 1 because we're inside the unit circle. So let's come down here. So that means we have A root 2. So that means this is going to be the length of A. This is going to be the length of A, and this is going to equal A times the square root of 2. So what I want to find, though, is I want to actually find the exact values of these things. So to do that, I'm going to need to solve that thing for this value of A. So the one that I get that I have to solve is A root 2 equals 1. Now, how do I get rid of that root 2? I've got to divide it. So I get 1 over the square root of 2, and I'm going to have to rationalize again. So I got to multiply that by the square root of 2 over the square root of 2. Bottom is going to give you a positive 2, and the square root goes on top. So that means this A value right here is the square root of 2 divided by 2. So that means our x length down here is the square root of 2 over 2. This one is also the square root of 2 over 2. So this has value square root of 2 over 2, square root of 2 over 2. So what that means when we go through and we find our exact values right here. Sine is related to the y, so the y value here is root 2 over 2. That's our answer. Cosine is the x of that coordinate, square root 2 over 2. Now tangent, I need to divide these things. So when I go to do tangent, I have to fill that in. I'm going to take the square root of 2 over 2 divided by the square root of 2 over 2. Those are the same number. Doesn't matter how complex they look. So two things that are the same thing, and we divide them, we always get 1. So the tangent of 45 is 1. You can verify those things by plugging in your calculator. You're not going to see square root 2 over 2. You're going to see 0.707 and some other decimals. But if you plug in square root of 2, then divide it by 2, you'll see the same number. But we do need to get these exact values. All right, last one for the first quadrant. We want to find this thing if we rotate 60 because it's our last spot for our exact values. So the same premise applies here. Put our 60s down here. So that's 60. Up here is 30. Now if we go back to our special right triangle, we only have 2 of them. So which one is this one? It's still this first one. But instead of putting the 30-degree angle down here for our angle of rotation, we've now put the 60 degrees in here for our angle of rotation. So we still have the same relationships in the sides, they're just in different spots. Across from the 60 is where we see the A root 3. So across from the 60 is where I get the A root 3. If we go back and look again, across from the 30 is the A. And this is still 2A. So 2A is going to equal 1. That's what this one tells us. So we're going to get the same thing for A. We're going to get 1/2. So when we go to find this coordinate up here, we actually still get the same lengths for A and A root 3. This is going to be 1/2. This is going to be the square root of 3 over 2. 1/2 down here, square root of 3 over 2 here. So this is 1/2. This is the square root of 3 over 2. Notice that that coordinate, the x and the y, is flip because we just oriented the triangle differently when we put it in there. So what that means is, if we look at our answers, the sine of 60, sine is still related to the y, sine of 60 is the square root of 3 over 2. Cosine of 60 is the x, it's going to be 1/2. Now we still need to do that division, okay? So we got to take the square root of 3 over 2 which is the y. We're going to divide it by 1/2 because we're finding the tangent now. We've got to always take the x and the y and divide them. So we're going to keep change it, flip it again. Square root of 3 over 2, 2 over 1. And this one's a little bit easier than the last one. That 2 cancels. And what do we end up with here? Well, that 2 cancels. We get square root of 3 over 1. No need to rationalize. Square root of 3 over 1, that's square root of 3. So our tangent of 60 is the square root of 3. Now, we're memorizing these things and all that comes into the payoff because we will talk about memorizing these and working through this, is that once I go past this, let's say I wanted to do 135, okay? And we'll get to the other ones with 210 and stuff. So this is an angle of rotation of 135. But when I look at the triangle here, and let me draw a triangle real fast. It doesn't matter when I actually look at the triangle for the triangle trig where it's at. But the angle that I want is I want this one. That's not the 135. This is my theta. What's in here is that theta prime, that reference angle, meaning that this triangle actually appears over here as well. I just have to adjust the values that I already know for this coordinate. So this is the second quadrant. So what we've learned in the beginning, theta prime is, let's go back and look at it just to make sure we get it right. If we go back to our reference angles in the second quadrant, we took 180 and we minus theta, right? So I went the wrong way. So here we're going to go, well, to find this angle inside the triangle, because this is theta prime, I need to do 180 and I need to minus 135 because that's the actual angle of rotation, but I want what's left over part. That tells me that this triangle is formed with a 45-degree angle right there. So that means that this spot is actually 45 degrees. This one is 45 degrees. I know this length is 1. We've already done all the math for this. 45, 45, 90s, we know these other two sides are the square root of 2 over 2. It's going to be the same length. It's the same triangle. It's just in a different position. So that means that this is the square root of 2 over 2, square root of 2 over 2. But what's different? Now you got to think directionality on the coordinate plane. To go left from the origin, that makes this thing negative. So that means this becomes negative right here. The x does. Does the y change? Nope. Y does not change. Let me adjust my brackets here, hit it off a little bit. So that means when I actually go through and I find these answers for 135, they're related to, I see the same numbers appear as I did for that 45. But now, when I look at this sine, that was the square root of 2 over 2. But for this one, what I see is that cosine is the negative square root 2 over 2, which is slightly different. Now tangent, I'm going to get the same number for tangent because I'm still going to take the y and divide it by the x. And those are still the same numbers. But this one's negative, meaning this one's going to give me negative 1. And that actually makes sense because that comes back to the all students take calculus definition. Since I'm in the second quadrant, all are positive here, students are positive here, which is sine. The only one that gives me a positive answer was sine. The other two became negative. But if I look value-wise, I still ended up with the same answers that I did here. I just had to adjust the sign based on the quadrant that I was in. So let's take that one step farther. I'm actually going to get rid of this. We're going to do something a little different. Let's take this same definition, this 45-degree angle, and let's say that this is in the third quadrant. So that's going to be 225 degrees. So let's do this for 225 degrees for our theta. That means if we were to draw this out, draw our angle of rotation here. (225 degrees takes us over here into that third quadrant. And that is our angle of rotation. Now the angle that we want inside our triangle, that takes us out to our point down here, is this little one. Since we're in the third quadrant, we learned that our reference angle is, let's go back and look at it, see if we can. Third quadrant, our reference angle is our angle of rotation minus 180 or pi. So we're going to take our reference angle of 225 degrees. We're going to minus 180 from it, and like we supposed, that's a 45-degree angle, meaning that inside this part of the triangle right here is a 45-degree angle. This is a 90. This one's a 45. It's the same setup here. So I know that the numbers for the lengths of the side are going to be the same. But what's different is, because I'm in the third quadrant, that's got to be negative and negative. It's the only way I can get down there. And it follows our setup. All students take calculus. The only thing that's going to be positive down here is tangent. So when we write our answers for this, sine of 225 degrees, cosine 225 degrees, tangent of 225 degrees, we get the same numbers out of this stuff. We're still going to get a 1, a root 2 over 2, and a root 2 over 2. But because I'm in the third quadrant and x and y become negative, that makes these answers negative, and tangent becomes positive because it's a negative divided by a negative. This would work with all the 30-degree reference angles and all the 60-degree reference angles, and so on and so forth. And we are going to spend more time on this and put this into a nice pretty picture called the unit circle that we'll kind of go through and memorize, and it helps us see some of the trig relationships that make the graph, okay? We're going to spend 2 days on this stuff. I imagine you're probably going to need some help. Do get online, find me those Monday, Tuesday, Thursday, Fridays, and we'll sit down, we'll work some of these things together on video chat, okay? See you guys soon.